So first thing, a word about the name. The acyl word, it's an old, it's part of the old naming system of chemistry. If you went back 15, 20 years, or in fact, if you look at a bottle of vinegar today, it'll probably say it contains acetic acid, where that acetyl or the acyl part of that means the acid contains that group. And of course, acetic acid would be that. So nowadays we call that ethanoic acid. So we're using the IUPAC naming system, which always goes by the number of carbons. But the acetyl or the acyl, I'm just going to call it acyl, but acetylation is the same thing. Means we're adding that group. So the addition of that group to a molecule is known as acylation. So that's where the name comes from. You don't have to worry. I mean, no one's going to ask you to name things in, old world English. I don't know when IUPAC came in, but I've been calling that ethanoic acid for my entire life, including when I was at school in the 80s. So acetic acid is very old. No one uses that anymore. But it's still around in terms like acylation. So acylation is adding that group. Now I'll talk about acylating agents.
Very sorry to disturb your lessons, sir. This is a lovely young man with a test somewhere.
I'll just stick him at the back.
Thank you very much.
Yeah, I'll talk about acylating agents later on, but the main one I'm going to use is this chappy. So it looks very like ethanoic acid, except I've swapped the OH for a chlorine.
So what would you call that?
Right, so the functional group, so we've got a new functional group, notice, which is that. Is called an acyl chloride, although of course you could put bromine or fluorine or iodine on there. So strictly it's an acyl halide, but we're not going to consider anything other than chlorine in our work. So naming a specific acyl chloride like this one, well, again, IUPAC rules say we use the number of carbons, so it has to start with eth, and like ethanoic acid, we have ethan for our thing here. It's not called ethan. And the name ending for our new functional group, our acyl chloride, is oil, O-Y-L. So it's ethanoyl chloride. Ethanoyl chloride. So if I had a couple of carbons, COCl would be another way of writing it. That would just be propanoyl chloride. Okay, so oil chloride or anoyl chloride, if you want to think of the name ending as starting there, with eth telling us that we've got 2 carbons. Okay, so let's have a think about this. We know that it's nice. We know that oxygen is a little bit electronegative, so it withdraws electrons away from the carbon. Chlorine is electronegative as well. About the same, hey?
don't know where this is going.
Mechanisms.
Yeah, we're definitely heading to a mechanism, definitely. So the chlorine's withdrawing electron density away as well, so that means that the carbon is sort of super delta plus. It's got a partial charge, but that partial charge is substantially larger than it would be for ethanoic acid. And again, we'll compare them later on. But yeah, you're right. Anything which has delta plus or a delta minus in it in chemistry, in organic chemistry, must be moving us towards a mechanism. And let's have a look at the reaction first. Well, there's a reaction you know, so let's start with what you know. We know that if we take an alcohol, like methanol, and add some ethanoic acid, and what else do I need to pop in that test tube before I warm it up?
Catalyst.
It is a catalyst, very good.
Potassium.
No.
Sulfuric acid.
Yes, which type?
Concentrated.
Concentrated, okay. But yeah, it is a catalyst. So we need to pop in a little bit of concentrated sulfuric acid, just a few drops will do it. And what would I make there?
Methyl ethanoate.
Very nice. Methyl ethanoate or methyl ethanoate. Okay, great. Well, I could do the same reaction with ethanol chloride. I mix ethanol chloride with ethanol, I'll get exactly the same result. But I don't need a catalyst. Why don't I need a catalyst?
It's very reactive, so it can lose the chlorine at a low temperature.
Right, gorgeous. Yeah, because the carbon is more reactive or more delta positive, the reaction will go at room temperature with no catalyst. So, room temperature. We had to warm there, didn't we? There we are. Warm with. You might remember when I wanted to make a substantial quantity of the ester, I had to boil it under reflux for half an hour or so. So yeah, that's a reaction which goes slowly. It's actually reversible, in fact, so really should have the arrows there. Whereas ethanol chloride will react very quickly, pretty much instantly, really, as far as organic reactions go, because we've got a much more reactive carbon. Okay. So, well, there we are. We know the reaction. So let's get started on the mechanism then. Okay. So we know all the action's going to take place at our delta positive carbon. Remember, delta pluses and delta minuses don't have to be there in your mechanisms in the exam, but they should be in your head. Because if you remember that carbon there is strongly delta positive, then that will remind you that it's going to pull in electrons. Now, just to start, I'm going to keep things as simple as possible. I'm just going to have water here. The water's got a couple of lone pairs. Lone pairs of electrons get excited about delta positive carbons. So we can see where this is going. We've seen a mechanism which starts off a bit like this before. Where would our next arrow go according to that mechanism? From the double bond. So we're going from the middle of the carbon-oxygen double bond on to the oxygen. how are things going to look in our new molecule? Chlorine hasn't taken part in the reaction yet, has it? We've got a new bond between the carbon and the oxygen there. These hydrogens are still there, they haven't done anything. And then we've broken one of the carbon-oxygen bonds, but there was a double bond there to start with, so there'll still be one bond. So we're almost there. What else does this intermediate, as it's known, what else does this intermediate need? Intermediate is, between the reactants and the products.
Would the oxygen have a negative charge?
Which oxygen would that be?
The one that used to have a double bond.
Yeah, so we gave that oxygen there an extra electron on top of the one it had already contributed to its bond, so it's now a negative. Anything else?
The other oxygen be positive.
Exactly right, because that oxygen's contributed 2 electrons to a bond. Normally it would only contribute 1, so that oxygen's an electron down. Okay. What type of mechanism have we?
Nucleophilic addition.
That's nucleophilic addition. Okay, so that's an addition step there. And you're right, it's nucleophilic because the first strike came from the lone pair on the oxygen. Nucleophiles are, by definition, electron pair donors. Well, that's exactly what's gone on there, isn't it? The oxygen has donated an electron pair to the carbon. That's the first thing to happen. So we've got some nucleophilic going on there. I'll put it in brackets. I'll explain why that happens in a moment. Okay. Remember, addition reactions as well always break a double bond. Always break a double bond. Right. What happens next will amaze you. The next step is that lone pair, well, there is a lone pair, there's several lone pairs on that oxygen actually comes back and remakes that double bond again. Someone's like, what's the point of that? Okay. So we're going to have that double bond back. The chlorine then departs. So I'm going to break that carbon-chlorine bond and we're going to lose the chlorine completely. Now if I left it like that, we would have this, it would still be an intermediate. You can either show this next step as a separate step, or we can include all 3 arrows in one go. So I'll do it as a separate step first, so you don't have too much to think about. We've seen this kind of step before. In order for oxygen to get its electrons back, or electron, it can do what? We've seen it with nitrogen before in a mechanism. Yeah, you've seen this happen. How does nitrogen get its electrons back? So what do I actually draw in terms of curly arrows?
One from the bond between there. No.
Yeah, that's right. Keep going.
The bond to the nitrogen.
That's right. So you've seen that before. From the nitrogen-hydrogen bond to the nitrogen, something similar happens here. Okay, so we can either write that as a separate step, in which case we'll end up with this. What have we made? Ethanoic acid. Or we can incorporate that step in here. Okay, and then you would just go to ethanoic acid would be our final molecule. I'm going to leave it like that. I think you can handle 3 curly arrows in one diagram. Gets it all done in one step. Okay. What type of mechanism takes place here in this second step?
Elimination.
Right. Elimination is any reaction where we're making a double bond. Addition, we're breaking a double bond. Elimination, we're making a double bond. So this step here is elimination. Okay. So we've got addition followed by elimination. So that's what the mechanism is called. It's just called an addition-elimination mechanism. If you want, you can call it a nucleophilic addition-elimination mechanism, but since there's no other type of addition-elimination mechanism, we don't have to specify the nucleophilic. We could just call it addition-elimination. Okay. None of this is particularly useful, has to be said, because ethanoic acid is fairly cheaply, readily available, comes in large containers, and it's very cheap. Whereas ethanoyl chloride is quite expensive, reactive reagent, which we use for special reactions. In fact, this reaction happens when we don't want it to. If the ethanoyl chloride gets wet, so if the lid's a bit loose, that would all it take, in a slightly damp storeroom, then our ethanoyl chloride is going to slowly turn into ethanoic acid. Not useful. Something expensive and reactive is turning into something cheap and less reactive. So let's change something. Our reaction here stated the reaction with methanol, so let's turn this into methanol. I'm literally just going to put a CH3 there. Now, if we follow the mechanism through, we can see we've got the mechanism for this reaction. Because, sorry, I should have changed the other one, shouldn't I? It's the wrong one. Okay, we'll change that one up there. There we go. Same thing. Now when our methanol reacts, we'll make this intermediate. And then when we lose the H there, we'll make that ester. And again, as I said, if the water reaction happens instantly with no catalysts and no heating required, then that one will also happen fairly readily. You just have to add the two reactants together and the reaction goes. Okay. So that's our addition-elimination reaction to make an ester from an alcohol and the ethanoyl chloride. Are you okay? Okay. Right. Time for you to have a go at something. You all got that written down? Okay, I'm going to get rid of all of that. I'll leave that arrow there and that arrow. I'm just going to change our water or our methanol to ammonia. Could you follow that mechanism through and give me the structure of the product that would make, please? Okay, what does my intermediate look like?
H3C. You like?
Hello, Benji.
Why have you got two jumpers which aren't?
Well, I was doing my.
Yeah, they told me. How did it go?
Fun.
How did it go?
Not that bad.
Right, we're kind of in the middle of something here, but you can review it because it's all going to be on YouTube later. What does this look like? Come on, Sean, talk us through it.
Would be a single bond to the oxygen, which is a minus, and then a single bond to the chlorine on the bottom, and then NH3 on the single bond again.
Okay.
And then positive N.
Okay. Tom, could you describe what happens next?
You do an arrow from, well, I did it from the bottom right hydrogen.
Bottom right,
to-
okay.
Going to the nitrogen.
Okay. It doesn't go from the hydrogen though, it goes from
the bond. in
from the
middle of
bond, yeah, from the middle of the bond to the nitrogen. That's right. That's one. There's three, remember?
There's one from the negative
You break the double bond, and then the next step, you remake the double bond.
oxygen at the top.
Where does it go from precisely?
It's all
The middle of the bond.
No, it goes to the middle of the bond. Where does it go from?
From the negative oxygen.
No. Remember, our curly arrow is always the movement of a movement of a pair of electrons. Yes.
Yeah.
So
There's no double arrow on that.
no. So let's draw some in.
Oh, okay.
Okay. Okay. Now we can put in the arrow. All right. Grand. One more.
Is there one from the chlorine?
Be precise. Where does it go from?
The middle of the bond to the carbon.
Not to the carbon. No.
Oh, to the chlorine.
Yeah. If you think about that carbon there, it's gaining something and losing something. If it gained 2, it would end up with, I don't know, 5 bonds. If it lost 2, it would end up with only 3 bonds. So gain something, loses something. So we've got our oxygen double bond back. We've lost the chlorine, sorry, I'm not drawing that. What we have here now is NH2. So that's another new functional group. That's where we have a C double bond O and an N. It looks similar to a C double bond O and an O, like an ester, and it is. And it's a kind of a linking a linking functional group between one group of carbons and another group of carbons. We'll come to that in a moment. It's called an amide, not to be confused with amine. Amine doesn't have a carbon-oxygen double bond in there. Amide does. To name our amide, well, it's ethane again. He comes up a lot in this section of the topic. And the name ending for amide, helpfully, is amide. So he's just called ethane amide. Right. Okay. All right. It's the third variation. I'm going to do one more. Do you remember what we did with water? We started off with water here, didn't we? I had water like that. And then I changed one of the H's and swapped it for a CH3. Now we're going to do the same thing, but with ammonia. What is that? Well, let's just write it in a more normal way. CH3 and H2. When we've just got a carbon and a nitrogen attached, what's that called?
Methylamine? No.
Well, it's methyl something.
Nitrile.
No, that's a CN as a nitrile. Amide is with a CO. Without the CO, it's amine. So that's an amine. Bye. Hope you learned some chemistry. Okay, so just like an alcohol's kind of like a substituted water, and amine is like a substituted ammonia. More on amines later, well, in the next topic. But again, let's just follow this through. I don't actually have to change any curly arrows, do I? In fact, the curly arrows have remained the same for all 4 examples, of course, because they're variations on the same mechanism. What do I have to change? Well, here, what do I change?
There's no oxygen.
There's still an oxygen.
Oh, no, in the
The H at the top.
CH3.
H at the top is a CH3. What about here? Well, that's now, that nitrogen has got an H on it and a CH3. That CH3 has stayed there. What's that called? Well, it's still an amide. Notice when I drew the amide here, I didn't put anything on it. I just put a couple of lines there denoting that that nitrogen's attached to other stuff. Could be hydrogens, it could be carbon groups. So it's still an amide, and it's still a 2-carbon amide, so it's still ethanamide. But now we've got this chat to take care of. How do we name him?
I was thinking ethan, methan, nitro. Amine.
The trouble is, let's just name this first. How would I name that? Not 2. Right, because the big functional group is automatically carbon. 1, 2, 3. So yeah, 3-methyl. Keep going. Butaname. Amide. Butanamide, because we've got CONH2. Remember, just an NH2 on its own would be an amine. CONH2 is an amide. Okay, so 3-methyl butanamide. It's 3-methyl because the methyl group is on carbon 3. Where's the methyl group?
On the last one.
It's not on any carbon at all. What's it on? A nitrogen. Okay. So that's how we write it in the name. Capital N standing for nitrogen, as it does. It's the chemical symbol for nitrogen. It's N-methyl ethanamide because the methyl group is on the N. It's tricky, I realise, but it does make perfect sense. Here, methyl group is on carbon 3, so it's 3-methyl. Here, the methyl group is on the N, so it's N-methyl. What could be more logical than that? Okay. Let's just make it a little bit more interesting. I've changed that to make that. Would anyone like to name that one?
Where?
This one here. I've just added another CH3.
Yeah.
Which? What? Who?
N-methyl.
You could call it N-methylamine. It usually just goes down as dimethylamine because there's no other place to put the methyl group other than on the N. Okay, so we've now got dimethylamine. Can you follow that through until you get a product? And then can you tell me what the name of that product would be? You can just write the product, but follow it through in your head. So you've got a product.
So for additional elimination, central
came in just at the right time, so he gets a bit of
I'll copy it all down.
gets a bit of mechanism fun. So our second methyl group would be here as well, and we lose that H, and so we'd have a second methyl group there.
Is it N-D-methyl methylamide?
If I put a second CH3 there, what would you call that?
3,3 dimethyl. So N-N.
That's it, you've got it. So this, I've now got two methyl groups, yes, so dimethyl, but it must be N-N, just as you have 3,3. I'm getting a bit confusing. N-N dimethyl ethan amide.
This is a bit less confusing though.
Okay.
Yeah, it's simple.
Just going to finish with a bit of stuff about aspirin.
Let me get to make that.
You do get to make aspirin, yes.
Do we get to take it?
Definitely not.
No neutral.
Although the way we make the aspirin actually ends up pretty pure. We've had our samples tested, and they
98.8% pure.
they come in about 90% pure. Yeah, no, I mean 99% pure. Sorry, but it's the other 1% that's going to kill you.
1% can kill you without proving you.
Right. Let's just
I know.
let's just have a look at aspirin. You don't need to remember this. We will get on to benzene rings later on. That's a benzene ring. Don't need to worry about that. Okay. That is salicylic acid, which I can't spell. Spell salicylic acid.
Oh, is that one we did
Salicylic acid. Is that right?
Yeah.
No.
Just
Well,
useless.
it's got I's and Y's in places that I can't remember. Sally is, yeah, that is right, yeah. Salicylic acid. In order to make aspirin, we start with salicylic acid, which, by the way, is found naturally in willow bark. And we add to that, I'm just going to put my acyl group at the moment. There it is, my acyl group. And that is, well, it used to be called acetyl salicylic acid, but we'll just call it aspirin. Okay, so we've got the OH group on the benzene ring. Again, don't worry about what a benzene ring is. It's just a thing of carbons there. The important bit is we're taking an OH group, adding our acyl group, and we're making aspirin. So you can see how that is acylation of salicylic acid.
Is that just like one step?
Oh, I wasn't clock watching. Okay, we're out of time, aren't we?
That's only 4.
Eh?
It's only 4.
Yeah, I need a little bit more time. Okay, I'm gonna stop there. That's still quite a good example of acylation, so it's not a bad place to stop. But there's a bit of work going into what acylating or acylation agents we need. So I'll leave it there, and we'll come back to this another time.